let's take a look at a situation where this all fails. Because of course we want to know, what do we do then when this is not an exact equation? So once again, we identify the pieces. This is m of t comma y, and this is n of t comma y, times y prime. These things added together do give me 0. It matches the template. So coming back up here, I just have to show that it's an exact ODE and psi exists if and only if I can take the derivative with respect to y of m, and that's going to equal the derivative of n with respect to t. So if I take m to find m sub y, I'm going to take the derivative with respect to y of m. That's going to give me the derivative of 3ty. 3t is a constant. The derivative of y is 1, so this will be 3t. And the derivative of y squared is 2y. Now n sub t will be the derivative with respect to t of n, which is t squared plus ty. Now the derivative of t squared is 2t, and oop, they're already not the same. Y is a constant here, so factor that out. Derivative of t is 1. Y times 1 is y, and these are not the same. Not the same. So ODE is not exact, and psi does not exist. So we're kind of stuck. We found an equation where our method fails. So what if a nonlinear first order ODE is not exact? Well, the beauty of this, and the reason I've introduced this method now, is because we can incorporate a factor, an integrating factor, just like solving first order linear equations. We can say, well, if we're off by something, maybe we can multiply both sides by this integrating factor. In this case, notice that mu, in our previous case, it was only a function of time, and it was something along the lines of e to the negative integral of a of t dt. In this case, we're going to allow for the possibility that mu could depend on t and or y to get the right factors in there, which, as we know, is called the integrating factor. So if you multiply both sides of our differential equation by it, there's m plus n y prime multiplied by mu, and then mu multiplied, I should probably put a multiplication sign here, so it doesn't look like mu of 0. And I'm just avoiding the extra notation here, so we'll just keep it as mu. And so when that distributes through, we'll have mu m plus mu n times y prime equals 0. So if mu has made everything work out, right? So now mu m is a new function. This piece right here is a brand new function. And mu times n is a brand new function. So we could think about these as kind of our mu m is a revised m function. And same thing with mu n. Mu n is a revised n function. And so still the same thing holds here. We'll be able to use that multivariate chain rule as long as the derivative of this guy with respect to y is equal to the derivative of this guy with respect to t. Don't let that throw you off that it's mu m now. That's just some brand new function. And all we've done here is we've just scaled both sides of the equation to incorporate the piece that we need. Now, how do you calculate what the derivative of mu m is with respect to y? Well, this is a product of two functions that both involve y potentially. So f prime g plus f g prime using the product rule, the derivative of mu with respect to y times m, plus mu times the derivative of m with respect to y. Now the derivative of mu times n is derivative of mu with respect to t times n plus mu times the derivative of n with respect to t. And this is just product rule right here. Next, and we're almost there, next we can actually try to solve for mu. So to solve for mu, we need to isolate it. So if we move all the mu terms over to the left-hand side, we see that from the second term here and the fourth term here, we can factor out a mu, leaving us with my minus mt times mu equals 0. And then I'm just left with my mu y times m, my mu sub t times n, negative. And now I can try to solve for mu. But wait a minute, this is too complicated. This is really tricky to solve for mu. I have two partial derivatives in here, so this is a really nasty differential equation. I'm sorry to use that terminology. I know nobody likes to hear that something is nasty, but you know, it really is. Look at this thing. This is the derivative of mu with respect to t times n, and then I have plus my m sub y minus n sub t. Now, fortunately, these two things I can calculate. Those things, m and n, are given to me. So I know those, I just don't know mu. Therefore, if I don't know mu, I don't know d mu dt, and I don't know d mu dy. So this is a very tricky equation to solve for mu, since it has two partial derivatives in the equation with respect to different variables t and y. So if one of these was gone, though, that would make our lives a whole lot easier. So let's just only focus on situations where mu ends up being a function of time alone. That it depends only on t. Then that would mean that mu sub y equals 0. Why does it mean that? Well, if mu, let's just say for example mu was 5t squared plus sine of t, and I took the derivative of mu with respect to y, so notice it doesn't depend on y at all. Well, the derivative of anything involving t is going to be 0, which ends up giving me d mu dy equals 0. Doesn't matter what these functions of t are. So that means this term here, right here, pops out because mu sub y is 0, so that term goes away, and we're just left with this stuff, which is right there, equals 0. So where do I go from here? And if I now rearrange this equation a little bit, first of all, negative d mu dt is, or negative mu sub t is negative d mu dt. Now, the reason I can write not the partial sign is because I know that mu is only a function of t. It's not a multivariate function, by assumption, plus my minus mt times mu. And if equals 0, if I move d mu dt over, I have d mu dt equals, I'm sorry, this is times n though, it's an n there, n times d mu dt equals my minus nt times mu. And now if I divide both sides by n, I get d mu dt equals my minus nt over n times mu. Now, this all right here is a function not involving mu, and this function here is a function involving just mu, so this is a separable differential equation. And once we know that value of mu, all that we have to do is multiply it to the m function and the n function and go about solving this the exact same way we just did. The only step here that is extra is to find the value of mu first. So this is an important equation to keep in mind here. And I know there's a lot happening here, but you have to focus on the piece by piece.